Everybody, so what is the data set for the team project? What is the data set? What is the data set for the team project? All states. All states. Just one of you. So I want you to read the data set in R, everybody, and tell me what are the dimensions. What are the dimensions for the data set? How many rows, how many columns, how many observations, how many variables?
That's
97,000 rows and 25 columns. Exactly. That's great. So for the team project, you need to analyze the data, make some models. It's going to be up to you what you want to predict. Ideally, you want to make two models. One linear regression, multiple linear regression, predict something that is continuous, and one logistic regression, predict a binary variable. So choose a binary variable as the dependent variable for logistic regression, and choose a continuous variable as a dependent variable for the multiple linear regression. So build two models, at least, I think. And then run the results, do some diagnostics regarding the assumptions and requirements, see what the model violates, how you can fix them, and yeah, make some diagrams, and then start the report. So you should write a report. You should start with introduction, explain what the data set is, and explain the models that you have built, the things that you want to predict, and then you present the models, then the results, then the diagnostics, everything. Okay. After you write the report, you will work on the PowerPoint. And so you should build a good PowerPoint that just summarizes the findings that you have had, the most interesting and the most important parts of the report. And then you should practice. You should practice presenting the PowerPoint. You should practice together and present it to yourselves. And in the presentation, of course, everybody should participate. So everybody should be here and participate in the presentation. And yeah, so you should assign tasks to each other. You should decide who's going to do what part, and who's going to present what part. And yeah, so what part of the report is going to be written by who? No? Any question? So I have not put a very rigid structure for the report for you, because I want you to be free to do whatever you want, and I want it to be flexible. So your reports are different from each other. I want to see different kinds of reports, and it's going to be up to you to choose the dependent variables and the independent variables. Essentially, most of the things are going to be up to you. Is that good? I just give you the data set. Go ahead. No, it's up to you. So you should decide what variables are related to that dependent variable. You should think about it from some theoretical perspective. You should provide some reasoning that we chose these variables as the independent variables because we thought that they can predict the dependent variable. Two models, two dependent variables, that means two models. So one of them would be linear, one of them would be logistic, ideally. But you may have two interesting linear models, that would be also fine. Or you may have two interesting logistic models, logistic regression models. Have you had any course with a team project before? Anybody? You have had a course with a team project? What course was it? Public speaking. So it didn't have a report or anything.
Just like a PowerPoint presentation.
Just a PowerPoint presentation. Okay, so you have experience presenting to a class. Who hasn't had any experience like that, a presentation experience? So all of you had that experience presenting to a class. Great. So, but I think this is your first serious team project, right? So that's going to be a very good experience for you. Okay, so if you don't have any question, I'm going to finish the script that I started on Monday, and we're really done. So we were talking about prediction and cross-validation. As you can see, we have, so we are using the packages data set. We already talked about it. That's the packages data set. We have, oops, the working directory should be the course data. So the packages data set, the number of rows would be the number of observations, and we can use the function nrow. Nrow would give you the number of rows. 730 days. So we talked about splitting the data into training and test sets. How large should be the training set? 70% of the data. So it doesn't have to be 70% all the time, but usually we use 70%. So that means we need to have 511 data points in the training set. Okay. And since it is a time series, the first part of the data set will be used for training. That means the older part of the data set, the older points, or the earlier points. So just think of it like this. So we have day 1, day 2 to day 730. We get the first 511 days. We take the first 511 days and use them for training. And we estimate the equation model using only the training set. Then we have estimated the coefficients and the equation model. We use that to predict the dependent variable in the test set. And how many data points do we have in the test set? From 512 to 730. 219 days will be left for the test set. So the older data points, the later data points will be used for testing. So in code, it's going to be something like this. Training would be from 1 to 0.7 times n, 511. test would be set diff of 1 to n and train. So subtracting the training set, or actually not the training set, the indices for the training set from all the indices 1 to n. And length of the test set would be 290. So now we have the indices for the training set and the test set. What we can do now is that we can use the indices in the data set and get that portion of the data set that we need for training. Just D of train would be put into the training set, and D of test would be used as the test set. Okay. Now that we have the training set and the test set, we use the training set to estimate the coefficients. We use the training set to test the coefficients, to estimate the coefficients. So we use the LM function because we have a linear model. We train the training set, $sign, the dependent variable, tilde, the next variable plus the next variable. So we can just run the regression like this, or we can just put the variable names like this, and at the end we put comma data equals the train. Data equals the train. So at the end we specify what data frame we want to use for all the variables. For all the variables. So I'm going to run this. So these two are equivalent, essentially. And the summary would be like this. So we have 3 coefficients, all 3 are significant. Of course, we can get the coefficients using the coef list. We talked about it before. So the residuals are in the resid list and the coefficients are in the coef list. So fit $sign resid would give us the residuals. And how many residuals do we have for the training set? What should be the length of the residuals? The list of residuals. That's correct, 511. You know why? Because we have 511 data points. So 511. That's correct. So Sam. So you already got all the points, all the points. So now we want to calculate the residuals for the test set. For the test set, the residuals would be calculated manually. The fit will not give us the residuals for the test set. Fit will give us the residuals for the training set, of course, because it used the residuals to calculate, to optimize, the coefficients, etc., because it is least squared of errors. Errors means residuals. So we have the residuals here for the training set after $sign, dollar resid. But for the test set, we have to calculate them. We have to estimate them just manually. So what we do is that we estimate, or we calculate the predicted values or the dependent variable using the coefficients that we obtained from the training set, but the predictors that we have from the test set. So the coefficients are estimated from the training set, are estimated using the training set. We already have the coefficients, and then we use the predictors from the test set. These two predictors from the test set. You see, the test. And then we calculate the dependent variable, the values for the dependent variable in the test set. So this would be the predicted values for the test data set, the predicted values for the dependent variable in the test data set. So I'm going to do that. And what would be the length of that? The length of that list the predicted values for the test data set. So we are talking about y hat for the test. So residuals would be delta y, right? And delta y would be y minus y hat. So how many y hats do we have for the test set? 219, exactly. So we have 219 data points in the test set. So we have 219 y hats in the test set. And that means we have 219 residuals in the test set. But we have to calculate the residuals. We calculated the y hats, predicted values. And we can, to calculate to get the predicted values, we can just use the predict function instead of multiplying the coefficients and the predictors. We can just use the predict function. The first parameter in the predict function is fit, which includes the coefficients. So it gets the coefficients from the variable fit, which has all the information, all the results of regression. And then we have the two columns that we need, the two predictors. We have the values for the two predictors, percentage of rubber size, weather conditions. The test of those two predictors. Just take these two predictors from the test data set and give them to the function predict. That's how we do it. And it will give us the predicted values. And the result would be exactly the same. So these two are equivalent. And the result would be 219 elements. To calculate the residuals, we first need to get the actual values. Of course, we have the actual values because it is the test data set, and we already have the data in full. So the actual values are going to be the average hours per driver. The residuals would be the actual values minus the predicted values. Y minus y hat, right? And we have the residuals. How many residuals do we have? 219. So 219 y hats minus each other, element-wise subtraction. We will have 219 residuals. So, so we have the residuals for the training set and we have the residuals for the test set. We can make the histogram for the residuals for the training set like this. This is the histogram. And we want to get some sense of what's the error on average in the training set. If we just average the errors, the positive and negative errors will cancel out each other and we won't have a good estimate. So what we do is that we get mean of absolute values of the errors. So average of the absolute values of the errors. So, and the result would be something like this. 0.6. 0.6 would be the result. This is the average of the absolute values of the errors. To know if it is a large or a small number, we should compare it to the average value of the dependent variable. The average value for the dependent variable is 6.447. So that means if we divide them, that means the estimated value or the predicted value for the dependent variable has about 9% error. Okay, on average it has 9% error, 9.2% error, 9.3% error. Because the error is about 9% of the average value of the dependent value. Okay, so what about the test set? We should do the same thing with the test set. This is going to be the histogram for the residuals in the test set, and the mean of the absolute values of the residuals would be How much? .47, and the mean for the dependent variable is 6.5. Let's see what's the ratio. 0.8, 0.087. That means 8.7% of the dependent variable. So the predicted value for the dependent variable in the test data set has about 8.7% error on average. On average has about 8.7% error. So now we should decide if the model is stable. So the error, the average error in the test data set is smaller than the average error in the training data set. So is the model stable, consistent, not stable, not consistent? Who says the model is stable? Raise your hand. Who says the model is not stable? Raise your hand. So the model is not stable. So why? Yes, okay. So if the average error in the test set was much larger than the average error in the training set, then the model was not stable. However, it's not larger, it's smaller. So the model is stable. So Kevin is right. The model is stable and consistent. Okay? That means the model, the estimated model, can be used to predict the future, the data that it has never seen before. Okay, so how accurate is this model? We judge the accuracy based on the accuracy that we see for the test set, which is actually 8.7%. The more accurate models have a smaller value for this percentage, right? Now, let's do another example. This is the taxi driver example. So, taxi example, taxi drivers example. So, we did the taxi.csv, and how many data points do we have? About 500,000 data points, a little bit less than 500,000 data points. So this is not a time series. Since this is not a time series, we cannot just take the first part of the data for training. What we do is that we randomly select 70% of the data for and use it for training, and then we use the rest for testing. So how can we randomly select? We just use the sample function. Sample. Sample of the set 1 to n, all the data 1 to n. How much of the data? How many data points? What is the sample size? 70%. So the second parameter is the sample size. And then replace across false. That means we don't put back what we select randomly. So we cannot select anything twice. No duplicates. So the training set, the indices for the training set is obtained like this. And the indices for the test set is obtained like before, just subtracting set diff. So now that we have the indices, we can just obtain the sets. So the training set is the of the train indices. The test set would be D of the indices for the test set. And then we just run the model and linear regression. Of course, we can just use the data frame before each variable, or we can just put the data frame at the end like this, comma data equals the trend. So these two are equivalent. Ln fair as a function of distance, duration, and credit. Fair as a function of distance, duration, and credit. Fair is a dependent variable. So we have four coefficients that all four are significant. 4 including the intercept. So we see 5 residuals, the 5 first residuals like this. And of course, the residuals are from the training set, because we use the training set to build the model, and fit is the model. And we want to calculate the residuals for the test set. What we do is that we first calculate the predicted values for the test set. So we use the coefficients that we obtained from the training set and the predictors that we have in the test set. You see the predictors, distance, duration, and credit, 3 predictors. And we calculate the predicted values for the test set. We have the actual values already in the data set, in the test set. Fair is the actual value, has the actual values for the dependent variable. To get the residuals, we just compare the actual values to the predicted values. The difference would be the residuals. So residuals, test residuals would be the actual minus predicted. So now we have the residuals for the test data set as well. So we can just make the histogram for the residuals for the training set. And again, you can see what's the mean of the absolute values of the residuals for the training set. It's 1.49. We can compare the average value for the dependent variable, and we get 11%, 11.5%. So in the training set, the predicted values for the dependent variable have about 11.5% error on average. You know, they have about 11.5% error. What was the test set? In the test set, so that would be the histogram. Go to histogram for me. Yeah. This is the histogram for the residuals for the test set. Of course, it doesn't mean much because, you know, we don't have much variation here for fair. And the mean of the absolute values for the residuals for the test set would be 1.49. It's about the same. So this for the test. So for the training, it is 1.49, 46, 57. For the test, it is 1.49, 25, 21. So very close, very close. That means it is very stable, hopefully. So the percentage is 11.5 again. So That means in the test data set, the predicted values for the dependent variable on average have 11.5% error. 11.5% error on average. The predicted values for the dependent variable. So what's the decision? Is it stable or consistent or both? Who says that it is stable? Raise your hand. Who says that it is not stable? Nobody? Okay. So it is stable, of course, because the errors are very close to each other. That means the model that we built using the training set can accurately predict the data outside the training set, like the test data. Okay, outside the training set. And what is the accuracy of the model? 11.5. So 11.5% error would be an indication of the accuracy of the model. The lower values, the better. Good? Any question? Question? Go ahead. Oh, I just wanted to compare the histograms for the training set and the test set, and they looked similar. Kind of, you know, but you have to be more accurate, more precise. So to be more precise, we just calculate the mean of the absolute values of the residuals and compare the mean of the absolute values of the residuals. The test set, that would be the more precise measure. However, if when we see the residuals, when we see the histograms of the residuals, one histogram is like this, the other histogram is like this. Oh, we know for sure that they are not consistent, you know. So I think I finished the PowerPoint, right? Did I finish this part? What, choosing the model? No? I should have covered this part. So I have covered this part for sure. Yeah, I have covered this part. Good. Sure.
I don't know if you notice that. I can see the 15 or 20%.
Oh, that's a good question. That's a very good question. So you are asking, what is a good number for accuracy? What percentage is acceptable?
Yeah.
It totally depends on the context and on the situation. Sometimes you may tolerate up to like 20%, and sometimes you have a some critical sensitive situation and you cannot tolerate more than 2%. So it all depends on the situation. I don't think there is a rule of thumb for that. There is no standard for that. I don't know of any standard. Do you know of any standard?
You'd want to beat random guess typically. So are we doing logistic regression still?
No, it is linear regression.
Oh, linear. Okay, well then yeah, you're looking at an MSC then, so no.
So it is just subjective. It's just subjective. Thank you. So we talked about consistency and stability and accuracy. I should mention that when you want to decide which model to use, you should decide what are you going to use the model for. So are you going to use the model for interpreting the relationships between the variables. You want to explain what's the relationship between an independent variable and a dependent variable, or you want to interpret the coefficients. In that case, R squared is a good criterion. Higher R squared means a better model. You can make better interpretations. But if your goal is to make predictions, if you want to predict the dependent variable, then accuracy is important. There are more accurate models. More accurate, I mean lower percentage of error. Lower percentage of error would be better, would be more important. Generally, higher R squared is associated with lower percentage for accuracy. So better, more accurate models. But sometimes it is not the case. When you have an overfitting situation, you have a high R squared, but the model is not accurate. It cannot make good predictions. The model can make good predictions for the past, but not for the future. You know? And predicting the past is not that difficult. So the taxi example is like this. As you can see, the histograms are similar. The mean of the absolute values are 1.5 and 1.49, about the same. And since they're about the same, we judge the model as stable and consistent. And we use the results of the accuracy of the test set as the results, as the accuracy of the model. So the accuracy of the test set is used as a measure of accuracy of the model. Okay, the accuracy of the model is the accuracy of the model in the test set. Okay. So I should mention something important. When you don't have a time series, you have something other than a time series, like the taxi driver, like people, like stocks, things like that. And the data is not chronological. You randomly select 70% of the data for training, right? So each time that you do it, you get a different part of the data set for training. And as a result, you estimate the coefficients differently using different training sets, right? So you get different estimates for the coefficients each time. So a slightly different estimates for the coefficients. So if I run this example, this second example, the taxi example, again, I may get different numbers for the residuals, and I definitely will get different numbers for the residuals and for the errors and the percentage of errors and the accuracy. They're generally around the same values, but instead of 11.5%, I may get 11.2%, you know, because each time I am randomly sampling, I'm taking a random sample of the data, and each random sample can be different. Each time that I take the random sample, it can be different from the other. Okay, so keep this in mind. Any question? No question? So we are done with prediction and cross validation for linear regression, but after the spring break, we are gonna continue with cross validation for the logistic regression. And yeah, so happy spring break. Thank you.
I'm finishing the edits to my dissertation to get it off to my committee tomorrow and schedule my defense for 3 weeks from now. And I was looking at, wait, why didn't I include that table? I'm pretty sure I ran that table. Oh, that's why, because if I said results weren't significant.